All right, so this video is going to help you understand what's happening at the boundary between the different tectonic plates. Really, this is going to help you with the stop motion video that you're going to be making about all these boundary features. So here we go. There are two types of plates. There's continental plates, made of like the mountains and the dirt that we see when we look around on the continents, and there's oceanic plates. Now, this isn't the ocean itself, this is the ocean floor, the rocks that make up the very bottom of the ocean, that part of the crust. And they're both floating around on top of the more dense mantle. Remember, more dense things move downwards, less dense things move upwards, and that's why our less dense crust is floating on our more dense mantle. All right, our first type of boundary is between two continental plates. So you've got continent versus continent in a head on collision. Convergent means to collide, to hit each other square on. So as these two continental crusts hit each other, we have mountain building, okay? And I don't love this diagram because it shows that this continental plate is being pushed down into the mantle. And with two continents, that's not really what happens. For the most part, what you're getting is they're just smashing into each other and forming mountains up above the earth and also pushing equally down into the mantle. So one is not subducting or being pushed beneath the other. They're just colliding and forming gigantic mountains. You can watch these videos if you're going through this slideshow on your own. For now, I'm going to just move past. Basically, this video shows India right here, leaving the rest of Pangaea a few million years ago, cruising across the ocean at the whopping speed of an inch or two a year, and then colliding with this other continental plate, Asia. So we have the Indian plate colliding with the Eurasian plate, and that forms the world's biggest mountain range, the Himalayas, aka Mount Everest. That's formed from a continent-continent collision. Now, oops, we're not going to watch that right here, but when mountains collide, or I should say when continents collide, it folds the rock, it bends it, it warps it, because that's a lot of energy, right? Those are huge masses of continents smashing into each other, kind of in slow motion. Like I said, an inch or two a year, and it can bend and fold the rock. If you've seen bends and folds like this as you're hiking or driving through a canyon wall, there's a decent chance that it was created by tectonic plates crushing into each other at some time back in ancient history. When you get plates colliding, you get mountain ranges. Again, this is a map of mountains, and you see a ton of mountains and earthquakes happening right where India has collided into the Eurasian plate. It's not an easy process. These two continental plates don't just slide right past each other like butter. They're grinding and it's gritty, and every once in a while a whole bunch of energy is released as one plate jolts into another, and it creates a lot of earthquakes, really. All right. Our next type of boundary is continent and ocean. So here again, we have a continental plate over here on the right. It's just chilling there. We also have an ocean plate right here. Now, in this case, when these two plates hit each other, the oceanic plate is more dense. Like I said earlier, more dense things, they tend to move downwards. So as this ocean plate collides with the less dense continental plate, the dense ocean plate will be subducted, aka it'll be pushed underneath it. Now, what do we know about the mantle? It's kind of warm, especially the lower you get, like the deeper you get in the mantle, the warmer it gets. And as this oceanic plate is subducted or pushed deeper and deeper into the mantle, we'll say down in this region, it gets melted. Okay. Not all at once, but little by little, it slowly starts to melt the deeper it gets. Now, this magma is less dense than the stuff around it. And it's piping hot, right? And that hot, less dense magma, because of the pressure of everything else sitting on top of it, will be squeezed up through this coastline, basically, through the continental plate until it reaches the surface. And when magma reaches the surface, we call it lava, and we also call it a volcano. So volcanoes form on the coastline whenever an oceanic plate is diving underneath the continent. These volcanoes are basically reincarnated ocean floor. They existed for millions of years as the ocean floor, They got melted and then recycled back into volcanoes as the magma rose up through the edge of the crust. So we're going to have a volcanic arc or a volcanic mountain range right on the coastline, pretty much along this continental edge. We're also going to see trenches being formed. As this ocean plate goes underneath, it's not an easy process. It's kind of taking the continental plate down with it. Just on the edge, though, just this lip of the continental plate gets dragged underneath with the oceanic plate and it forms a trench. And this picture does not really do it justice because it makes the trench look so small and the mountain look so big. But in real life, these trenches can be 30, 35,000 feet. You could cut off Mount Everest, flip it upside down, and fit it inside this trench. Super, super deep. And that's just the edge of the continental plate being dragged down with the oceanic plate as it goes. Like I said, it's not an easy process. And as these plates grind against each other, we get earthquakes. So, ever heard of the Andes Mountains? Well, look where they are. They're right on this coast, this west coast of South America. And believe it or not, we're not going to watch that video here. You can watch it on the slideshow that you've got attached in Canvas. But here we have these plates. The Nazca plate is speeding towards South America, and South America is moving this way. And as they collide into each other, you got the ocean plate going that way, South America moving that way. This more dense oceanic plate grinds its way underneath the continent of South America, and it forms these mountain ranges, the Andes Mountains. And they are volcanic because they're made of the old ocean crust that's been recycled up through the lava or through the magma and kind of reborn as these mountains. You also get some of the world's worst earthquakes happening here. Here's what the Andes Mountains look like. They're gorgeous. They're also old volcanic mountains. Okay. If you looked at a map of earthquakes along South America, you probably wouldn't be surprised to see that a lot of these earthquakes, actually all of them in South America, happen to be right on the west coast. And now you know why. Here's a really terrible photo of the earthquakes in the area. Are you surprised that all these earthquakes are happening right on the coastline? Hopefully not, because they're happening due to this plate right here grinding underneath the rest of South America. Or I guess just this edge of South America is where it's going underneath, and that's why the earthquakes happen. Some of the worst earthquakes in the world are happening right here along this coast because of tectonic plates. Okay. Again, I said there is going to be a trench right off the coast. Okay, so you've got like the beach right here. You go a few miles off the coast, and there's a super deep trench formed by this plate sliding underneath. Let's take a quick look at Google Maps. You can see this, really, you can see this very clearly from the eagle's view, right? High up above. So these are all the mountains right here. Look at this dark line around the outside of the coast. That is the trench. Okay, that is the fold of the ocean plate diving underneath the continent, and it's not surrounding all continents. Like, look at this side of South America. Nothing. Look at this side, right? Not a deep trench really right here. Not at all, because the ocean is not being subducted under the plates right there. But look by South America. Bam. You got deep, deep waters right here formed by this plate being subducted under the other one. Okay. Get rid of that. All right. Next. The next thing we have is the ocean-ocean convergent boundary. Again, convergent means moving into each other, heading towards each other. They're converging or colliding. And here we have ocean versus ocean. Now, the actual waters aren't what's colliding, really. We're talking about the rocks underneath, right? The ocean floor. In this case, they're both really dense, but one of them's going to win out. One of them is going to be more dense and end up taking the low road, right? While the other one takes the high road. In this case, it's this plate right here. As it gets pulled underneath, as it dives down, it gets hot and it starts to melt. That melted rock ends up rising to the top because it's a little bit less dense and it's hot and it's under a lot of pressure. And it reaches the bottom of the ocean floor. Now it forms a tiny little underwater volcano, and every time it erupts, it makes that volcano a little bigger and a little bigger and a little bigger until it reaches the surface of the earth. Once it reaches, well, I should say, the surface of the water. Once a volcano reaches the surface of the water, we call it an island. Okay, this is how a lot of the world's islands are made, but not all of them. Okay, specifically not Hawaii, if that's what you're thinking. So we're not just talking one individual little volcano here making one individual island. We're talking about an island arc or a chain of islands. And this chain of islands follows the, the plate boundary all the way across where it's ocean versus ocean. So you're going to see this island arc or this island chain going all the way through the ocean in a line following the plate boundary perfectly. Because there's a plate being subducted, you also are going to see another trench. Okay, that's the edge of this plate right here being dragged down with this one as it goes because they don't come quietly. You're also going to find some earthquakes in this situation. Again, I'm not going to play this. You can do that on your own, but it's basically just describing what I'm describing. Let's take a look at Google Earth, though, because I think it's really cool. Google Earth is basically your proof that I'm just not making this up because you can see it from space. So let's look at where this is actually happening. You remember how, or have you ever noticed, I should say, how Alaska has this tail right here? Well, that tail is a bunch of islands. And right here, they're so close together that they basically form one long group that's all combined. But the farther out you get, the more spread out and smaller they tend to be, okay? Well, you should also be noticing right now this gigantic trench right next to them. What this shows us is that, I'm going to zoom out real quick. What this shows us is that this gigantic oceanic Pacific plate is moving upwards, kind of up into the left a little bit, up into the edge of this oceanic plate. So we got ocean versus ocean. And what do you expect? Well, you have a trench as this lip is being folded down on this plate's drag, down to the bottom. As this dives into the mantle, it pulls the edge of this plate with it. And you also see where this Pacific plate has melted, turned to magma, and risen back to the surface, forming this entire island chain. These islands are called the Aleutian Islands. And look how neatly they follow this ridge line. Look how neatly they follow this plate line. It's exact because they're created by the edge of the plate. So really, these islands are on their way all the way over to Russia. Like I said, this plate is kind of moving up into the left, or northwest, I should say. And so over here in Asia, we're actually getting some of the same action going on. See this deep trench right here? Super deep. This is actually where the Mariana Trench is. Deepest part of the ocean. 35,000 feet, if I remember right, roughly. Notice how there's a trench. And then what's on the other side of that trench? A bunch of islands, aka Japan. Japan is made out of a whole bunch of volcanoes really close together, or volcanic rock that is spewed out of volcanoes. And it is the result of this Pacific plate melting as it gets pushed underneath and rising back up to the surface to be born again as new igneous rock in Japan. Pretty cool. The reason Japan is kind of bent is because we actually have another plate, a little tiny plate right here, that's also moving that way. So you kind of have a double action plate going on right here. Okay, back to our plate boundaries. No, I don't want to play that. We already know what's happening. Okay, so when you have an ocean-ocean subduction boundary, you're going to have three main things: a volcanic arc of islands, a deep trench, and earthquakes. That's not the sun. That's a representation of earthquakes. Okay, it's very, very similar to ocean continent. Really, the only difference is instead of these islands, if it was a continent over here, we would just call them volcanic mountains. In this case, we just call them islands because they're out in the ocean. So really, this subduction and melting of this plate is what's causing these to be volcanic. It's why the Andes Mountains are volcanic, and the Himalayas are simply just piled up rock with no volcanic activity, because nothing was melted in the Himalayan continent collision because no plate was subducted. Okay, now we have two ocean plates going the other direction. Instead of moving towards each other, they're actually moving away from each other. It makes sense if on one edge it's moving into a continent, on the other edge it'd be moving away, right? So whenever we see this, it forms a ridge because this magma under here in the mantle, it is under a lot of pressure. And whenever a little bit of that pressure gets released because a crack in the crust opens, this magma can't wait to fill that gap. So along this ridge, with this plate moving this way and this one going the opposite way, it is slowly, inch by inch, opening up a crack in the middle of the ocean. And as soon as that crack opens, more magma rushes up and fills that gap. It meets the cold water and it hardens onto the edges of this plate, which basically makes it brand new rock attached right here to this edge. As it rushes up, it actually kind of pushes up on the edges of these plates. So if you see this feature out in the middle of the ocean, not only is all the rock super young right here, like brand new baby rock, but the edges are also pushed up into a ridge. We call this a mid-ocean ridge, and it's kind of like the spine of the ocean. It's slightly raised. It's not like a huge mountain range or anything. It's a slightly raised ridge that runs right down the middle of those oceans, and it's where new ocean rock is being created. New crust is being created here, so it's a cycle. For every inch of crust that gets devoured diving underneath the continent, we have another inch of crust being created at a mid-ocean ridge. Remember last week when I said there was 8 evidences of tectonic plates that we were going to learn about and continental drift? Well, ocean features was one of those evidences, and the trenches and the mid-ocean ridges and the age of the ocean floor being super young at the ridge and super old near the trench. These are all qualities of the ocean floor that led us to believe the continents are moving and there are tectonic plates that make up our crust. We never would have known about these trenches and ridges if we weren't mapping the bottom of the ocean floor with sonar. Okay, this is going to show basically what I just described, and here it is in a GIF. You got magma pushing up right here. As these plates leave and flow this way, it opens up a crack, and brand new lava cools down and forms new rock to fill the gap. It's like next rock in line, right? So no, I don't want to watch that right now. If you were very patient, and I mean like millions and millions of years patient, you could stand right here on this edge and you could get a free ride all the way across the ocean floor to the nearby continent, where you would be then subducted into an ocean trench and shoved underneath the continent to be melted in the mantle. I wouldn't suggest it. Also, it takes millions of years. Okay, when we have an ocean-ocean divergent boundary, like we're talking about, divergent, by the way, means moving in opposite ways, right? They're diverging, they're going opposite ways. Okay, you're going to get some volcanic activity. You see this spine right here, this line right down the middle of the ocean? Well, that's the divergent boundary. Here's the edge of the plate. As this plate moves to the left and this plate moves to the right, it's pushing these continents in opposite directions. That's why South America and Africa used to be attached here like puzzle pieces. And then as this crack opened up between them, it spread them apart inch by inch. You're going to see some volcanic activity at these boundaries, and you're going to see a few earthquakes as well. But they're not going to be super severe earthquakes because no plate is being subducted. Okay, like I said, here's the ridge. Here's like that spine that goes right up the middle of the ocean. It's the reason these continents have all spread apart, because it's pushing them away from the middle. And here's the age of the rock. So red equals young rock, and the green and blue equals the older rock. Notice how right here at the ridge, it's super young. But the farther away you get from the ridge and the closer you get to the continent, the more green and blue the rock gets. That's the oldest rock existing on the ocean floor. And eventually, like this rock right here is going to get kind of destroyed by the continent, right? The reason there's so much red right here is because, excuse me, this plate is spreading really fast, or this plate is moving really fast. which means a lot of this rock is young compared to the rock over here. That's why there's such steep mountains right here, because they're basically flying underneath as fast as they can. Okay, well, continents can also diverge. Remember a minute ago when I said that Africa and South America used to be connected, but they diverged? They went opposite directions, and now there's an ocean between them. Well, that is still happening. When two continents are moving in opposite directions, it opens up this gap between the two of them. You really should watch this video. It explains things really, really well right here. But basically, as they open up, the lava, or the magma, I should say, is now getting like closer and closer to the surface, right? Because as these pull away, they're kind of falling away in shelves. They're falling down to meet, I guess, to fill the gaps as they're pulled. And so you kind of have this staircase going down and up. And in the middle, you see there's some water forming, because when it rains, where do you think the water's going? Well, it's going to the lowest spot, which in this case is right here in the middle. As these get wider and wider and wider, you're going to see this gap in the middle get also wider, and slowly water's going to start leaking in from the ocean. At first, it'll be kind of like a river, or like just a little bit of an inlet, a little bit of a leak into the continent. But millions of years in the future, as these two plates get farther and farther apart, eventually the ocean will come all the way through here, and it'll be a little skinny ocean at first. But as they get farther and farther, it will open up into a full-blown, newly born ocean. This is like what happened with the Atlantic. There used to be no Atlantic Ocean because Africa and South America were connected to each other. But as they opened up, just like this, we'll say this is South America and this is Africa, eventually this skinny little ocean ended up widening into the Atlantic we have today. And the Atlantic is getting bigger every year, only by a little bit, but it's still opening up. Okay. So look at this map of earthquakes in Africa. There's a specific line right here where earthquakes are happening. Look at this map of volcanoes in Africa. You see a trend? There's something going on along this line that's causing earthquakes and volcanoes. Look at these cracks in the rock. See, like the way they're cracking? Like look at this three-pronged kind of peace sign looking type split that's happening in this dirt. Well, those are the angles that the rock is cracking in. Look familiar? Right now, we have this little inlet of water going this direction and this direction. The third crack is actually opening up right down this part of Africa, and it's causing all those earthquakes and all those volcanoes. Right now, it's still pretty small. Here's the crack right here. Just a tiny little crack with hills on both sides. But as the future unfolds, we're going to see this part of Africa actually spread apart and float away. It'll be its own island, completely separated, and this is going to become an ocean divergent boundary. And it'll open up until it's its own ocean, kind of like the Atlantic. And another ocean like the Pacific is slowly going to close because things are always changing. Our last type of boundary is called a transform plate boundary. This is when these two plates are sliding past each other. Not as much happens in a transform boundary, but we do get tons of earthquakes. I'm gonna watch this with you just so you get the main idea here. We know where a transform boundary has happened because we might have a mountain range that used to be connected that is now separated because the plates have moved. This is happening in places like California. You ever wondered why California is so earthquakey? Well, it's actually split onto two different plates. Same state, two different tectonic plates. This part of California happens to be moving down and to the right. This edge of California right here is moving along with the rest of the Pacific plate up and to the left. Okay? This is headed up and to the left. So California is split on both. This is what it looks like from the aerial view. This is the San Andreas Fault. And as these rocks grind past each other, you can get some major earthquakes. Eventually, will this part of California be moved up out here into the ocean? Yeah. Just, wait 100 million years and we'll see what it looks like. Until then, just build some earthquake proof buildings. Okay. This is a map of earthquakes in North America, or I should say the United States. The pink is the most severe, with yellow being kind of minor little baby earthquakes. Notice how California is just absolutely riddled with earthquakes? Yeah, that's because of the transform plate boundary. Now, this is an interesting thing up here. This is where Yellowstone is, and that's caused by a hot spot, not a plate boundary, but a super hot location inside the mantle that's basically busting its way through the crust. And that's why we have Yellowstone. Hey, that's all I got for you. Go through as you watch this slideshow on your own. Actually, watch the YouTube videos that I put in the slideshow because they're super helpful. And hope that helps with understanding tectonic plate boundaries. And good luck.